All right, welcome students. And again, we're going to deal with the last part of solutions. And this should not take us very long. Basically, what we're going to deal with is the last section of colligative properties. We already dealt with things like freezing point and boiling point and how that can be changed of a solution and how we can calculate that. And then we're also going to deal with what's called colloids as well. And we'll introduce all of that. The last thing that we need to deal with solutions underneath colligative properties, or that we're going to talk about for our purposes, is what we call osmosis. And some of you guys, I'm sure, if you've taken biology, have dealt with osmosis before, or even in other science classes, and you're probably somewhat familiar with the basic definition here, and it's the process in which a solvent moves across a selectively permeable membrane. Some of you, the definition you might have used before is, water moves across a selectively permeable membrane, because most times the solvent is going to be water. And in most of the examples we're going to use, that will be the case. And by selectively permeable membrane, we just mean something that's in between one solution and another. So you have two solutions, and they have maybe varying concentrations. In other words, you have a solute in each of those solutions, and one will typically be stronger than the other or more concentrated than the other. And the membrane, by selectively, we mean that it will allow certain things through, certain molecules through, and others not. So for example, let's say if you're talking about water and salt, sodium chloride. Water molecules are smaller, and so they can move across a membrane, whereas salt particles can't. They're bigger, and so the membrane would trap them on one particular side. And so only select things can move across the membrane there. And typically what happens is the solvent is going to move from an area of low concentration to an area of high concentration. So for example, if you have something, let's say, that has salt water, and you have something that is basically pure water, then what's going to happen is the area of pure water is going to flow through that membrane into the area that has the solute in it, the salt water, to decrease the concentration of that. So it moves from an area of low concentration of solute to high concentration. And there's a lot of different tests you can do this. Cells do this on a regular basis to maintain that area of concentration. Matter of fact, you have to be careful with cells. Cells can end up either bursting or drying up if the surrounding solution that surrounds a cell is either too high a concentration, then the water will flow out of a cell, or vice versa. If you have a concentration outside the cell that is very weak, then the water will flow into the cell because the solution in the cell is more concentrated, and therefore the cell can end up bursting. So you have to maintain a very, very controlled balance, which is amazing in terms of how we were created, because here you have a situation where the body needs to maintain a very precise balance in order to survive, and yet somehow it does. Osmotic pressure is simply the amount of pressure required to prevent osmosis from occurring. And basically, this is the idea that as water flows in across that membrane, eventually you reach a point where enough you've diluted, if you want to think of it that way, the solution enough so that water is going to want to begin to push back out across the membrane. And as you have water pushing in on the membrane and out on the membrane, eventually when that kind of reaches equilibrium, then that pressure will stop osmosis from occurring. It's kind of maybe a layman's terms. There's some big fancy terms, to describe this, how to, but that's kind of a real simple way to describe what's going on there. And typically, the higher the concentration of the solute, the higher the osmotic pressure that you have on a solution. All right, what we're going to take a look at now real quickly is just some basic terms, and that is when this is happening. You may hear of solutions that are hypertonic. One is a solution which means that's a solution that's more concentrated than what's on the other side of the membrane. So you have your membrane, and then you have what's on the other side of the membrane, or what's in that solution. Um, and the surrounding solution is more concentrated. We call that a hypertonic because the concentration is above. That's what hyper means. It's above whatever the other um, solution is that's on the other side of the membrane. A hypotonic means that it's a solution that is less concentrated than what is on the other side of the membrane. And then the last one here is what's called isotonic, when concentrations on both sides of the membrane are equal. Kind of a common example of this, and I think you even have a picture of this in your book, is if you go to the hospital, or if you've ever been to the hospital and they hook you up to an IV, typically the fluids that they use in an IV solution are more often than not isotonic, because they don't want to pump you full of stuff that's going to cause your cells to either have water, leave them and your cells end up shrinking, or water come across that cell membrane into your cells, and then your cells burst, because that could cause some very serious damage to your body. So they have to design solutions that they put in IVs as isotonic. That's important to the human body. So there's a lot of chemistry done even in something as simple as that. Well, I guess it's not so simple, but so that would be kind of an example where it's used in a real world situation. All right, the last section here, we're going to deal with what are called colloids, and the definition basically is they're small particles dispersed in a medium. A medium, can be just about anything. It can be, a gas. It can be, a liquid in a liquid. A variety of different things. In other words, you're putting one thing into another, and these technically are not directly solutions, because typically they are dispersed. Or they can be, in some cases, it's basically the difference between a solution and what's called a suspension. And we're not going to deal with all the differences there, but these are little tiny small particles, and it gives some very unique properties as we go through. And the first one we're going to deal with is what's called the Tyndall effect, which is the scattering of light by colloidal particles. And basically, the best way to illustrate this is if you take a jar of water or a glass of water, and if you want to do this at home and get a flashlight and you shine it through, you cannot, the light will go through the glass, but you can't see the outline of the beam as it passes through that glass. The glass may be brighter, but you can't see the outline of the beam as it goes through that water. Why? Because it's a solution, and it's just going to go straight through. If, however, you have little particles in there, in that water, that are colloids, bigger particles, enough to take that light and then scatter it, in essence. A good example of this would be fog, where you have little tiny water particles that are in the air, that are in the gas that we call air, and so they're mixed in with that. They're large enough to scatter, in essence, the light. And so, if you're driving and you have fog and you have your headlights on, you can see the outline of the beam through that. And so if you had a glass and you had a suspension, or not a suspension, some colloidal particles in there, you would be able to see, let's say you poured some milk, a little tiny bit of milk in water, enough to make it cloudy. You could shine and see the beam of light through it, because you have enough particles to break up the light there. Another one that we deal with, and kind of one of the last ones that we'll talk about, is Brownian movement, and is named kind of after the guy who discovered this, and basically discovered that this is the movement of particles because they're being hit by smaller particles. And this plays a role kind of in a couple different things. One, you can think of, if you are cooking something, let's say you're cooking bacon, because everybody likes bacon, and you're at the other end of the house and you smell that wonderful smell of bacon cooking, and oh, it just smells so good. Well, what is that? Okay, how can you smell it at the other end of the house or whatever it might be? Well, it's because, okay, as you have those little fat particles, and they're cooking, and some of them are released in the air and they're struck by little air molecules, and they're transported bit by bit, okay, through the air, okay, and eventually they reach your nose. Okay, and again, they're very small, okay, but they're big enough to be moved around by the air, and eventually they reach your nose and you smell the bacon cooking. Well, what is it you're really smelling? You're smelling the fat, in essence, of that bacon that's being cooked and transported. Another way we kind of see this might be an illustration of what we call diffusion. When, let's say you put some drops of dye or something like that, or food coloring in water. And you see it slowly diffuse throughout the water, and the water turns from being clear to blue. If you drop blue food dye in it over time. Okay, that would be as those little particles are striking each other. They do what? They disperse that. Excuse me. They disperse that food dye throughout the liquid because of Brownian movement as the different particles are being struck by even smaller particles. The last one we'll mention is emulsion, and this is a stable mixture of two liquids that are normally immiscible. If you remember, immiscible means two liquids that can't be mixed. Great example is oil and water, and probably the best example to illustrate this is mayonnaise. Mayonnaise is, two key things in there are milk, okay, and which is mostly water, and then you have oil, okay, like vegetable oil there, or sometimes it's like olive oil that it comes from, and those two don't normally mix, and which is why if mayonnaise goes bad or something like that, sometimes you'll see it separate. So why is it when you buy mayonnaise they are mixed together, somehow? Well, sometimes you're able to find a substance out there. In the case of mayonnaise, usually it's eggs or egg whites, I believe it is, that they use, that is able to latch on to the polar water and the non-polar oil and bring them together, in essence. It's kind of a simplified way of saying it, and it's able to cause them to mix and be miscible in one another. And so that would be the process we call emulsion. And that's basically some real quick concepts there dealing with solutions.